afternoon. If I'm gonna be speaking about game, well, after speaking and hearing all these talks, it's a little bit awkward to talk about some game. But still, when the project was proposed to create a game, well, it's like pursuing some sort of childhood dream. So it's really, really hard to resist not picking it. So Quantum Phase of Superposition Tactics is the name of the game. The name is quite fancy, but the inspiration came from classical role-playing games which are turn-based. So the player has some actions which he can perform in his move. The enemy's actions are driven by some sort of probabilistic artificial intelligence that is picking the moves for the enemy, but it's depending on the phase of the battle. And the superposition and the quantum states are actually acting as the main tool for deciding which action is actually happening in the battle. We're having four qubits only for this game. Two leftmost qubits are the player's side. Two rightmost qubits are the enemy's side. And we are linking all these possibilities with the actions from both sides. If on the player side there is a 0-0 after performing an observation, player is in the idle state and doing nothing. So theoretically, it is the least wanted state for us to observe for a player. If there is a state 0-1, the player is attacking, so dealing the base damage to the enemy. If the state is 1-0, player performing his defense, basically stacking some sort of defense factor to reduce the next received damage. And finally, there is a 1-1 for a healing. If this is what is observed, the player is restoring some sort of health points, but not going over cap. The same set of actions is linked with the enemy, but the enemy has a little bit of upper hand compared to the player. First of all, when the player is idle, he is not really doing nothing. He is charging his attack power. So doing idle, 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 enemy is stacking its attack power for the next attack. Then the enemy's attack is also changing through the changes of the phase of the battle, so it's growing stronger by the default. So, for example, if we had some sort of superposition or some sort of state, we performed a measurement and we observed the state 0-1, 0-0, then the player's character is performing the attack action and the enemy is doing nothing, idly charging up its attack. So the battle is split into phases. Phases are switching only once, depending on the health level of the enemy. If we're going beyond some threshold, the next phase is triggered. So at the beginning of the battle, the player has a full capacity of different quantum gates, which he can use to alter the state vector that we're having, either to go to superposition or somehow alter the probabilities of seeing this or that state. For rotational gates, Rx or Y or Z, allowed rotations are linked between 0 and pi, so from between 0 and 180 degrees. All gates are post-specific number of quantum points, basically the analogous of magic points. So even if you can use any number of gates per your move, you're still limited with this limit. And only 10 points of these cube points are restored per ending the turn. So you have to be careful with selecting the gates you want to use. Otherwise, you're going to run into a drought, the lack of these points. At the first stage, the enemy has very limited capabilities. Identity operator, which can use to only own part of the state of the enemy state, and X and other markings. There is no QP limitation for the enemy. When the next battle phase is reached, the enemy health dropping below 70%, the player is losing the access to the X gate. So it's becoming so-called sealed. Now you cannot easily alter the superposition into 0-1 from your side, especially if the enemy is going to use some sort of more sophisticated action. And now the enemy is also doesn't have access to the identity gate to nothing, but the enemy is having the possibility of using the gate, phase gate, and C0. C0 always controlling own qubits and targeting player's qubits. So there is no going to be this control and target happening from one side of a player. Herein, the enemy is starting to apply 2 gates per move. In the first phase, enemy can use only 1 gate per move. In the second phase, 2 gates applied sequentially to our state. Then, when the enemy's health is dropping below 40%, the third phase is triggered. Now the player is losing the access to yet another gate. Now the Adamort gate is sealed, and the enemy is increasing its capabilities of acting against the player. Now the rotational gates are introduced, which are linked and set the angles between pi over 8 and pi. Y is not 0, so we want to eliminate all close to 0 rotations for enemy doing something meaningful, not like go into this identity through rotating by 0 degrees, for example. Overall, we can say that the complexity of the superposition to evaluate is changing throughout the game phases. It's rather simple at the first battle stage, it's becoming a little bit more complex on the second battle stage, and it might become quite complex to work with at the third battle stage. Moreover, at each of the stages, we have different number of turns before performing evaluation. At the first stage, we are evaluating each and every turn, so you did some action, enemy did something, and then we evaluate. For the second phase, we waiting 2 turns until evaluation, so you have 2 turns to do something. You did something, enemy did something, then you're doing something again, responding to the enemy's action. Here in the third battle phase, there are 3 turns for the evaluation. So the superposition is growing more and more complex. Overall, the whole battle is kind of linear, but featuring 2 different endings. If the enemy was defeated, so the enemy's health is reached to 0, or the player was defeated. Technically, it's following the classical structure of such type of the games. Okay, and finally, I show a little bit of pre-recorded gameplay. It's a little bit simplified and quickened, but it's like a 2-minute. Okay, I muted it just in case. So, like, I won't hear anyone with the music. No. But nevertheless, of course, it's featuring some classical game features as the dialogues, which are going before the battle, after the battle, and in between the game phases transition. So after the introductory dialogue, the battle starts, the player can do something to alter our, let's say, state vector, or go into a superposition and things. So technically, what we want to do, we want to always to keep ourselves at the state 0, 1 for the player, but at the same time, we really don't want for enemy being in state of 0, 1. Plus, we also don't like to be, like, see enemy healing. Otherwise, our actions won't do much things. So we have got like 2 goals in mind to keep. And the enemy is responding for each of our moves. And this is phase transition. We're moving to the battle phase number 2. And after this, the player, as you can see, has lost the access to the X gate and has to use a different set of gates in order to go to the end of this game. There is one thing why the enemy is more overpowered compared to the player, because the strategy of just ending the turn and doing nothing won't work in most of the cases. Because at the same, for example, observed state, the enemy will rarely do more damage to the player than the player possibly can do. So that is the key concepts. Of course, there is a little bit much more to it from implementation point of view and from possible expansions, but that's it. Thank you.
Yeah, thanks. So basically, we expect some basic but good games, and some students really make it kind of professional level, and this is really fun of the game. Any question? I can take. Yes.
Well, considering it was my really first experience of doing anything on that scale and everything with the games, I spent approximately 30 hours to work on it. But it's including the time when I have to rework the code, because to change some things. Initially, I want to go with the gets, sets, and all this, and passing variables through different files, but it's turned out to be not the good idea for such a scale of the project. So I have to pull out all variables in the other file and keep them, let's say a little bit of global, in order not to pass too much parameters and so on, and rework in this regard. Like the most game was already done, and in order to implement the last features I want, like for user interface and things, I had to rework it from the scratch. So it took a little bit of more time than expected in this regard. But overall, conceptually setting the framework and understanding how different components should work, well, it wasn't that hard. Well, it's still a Pygame. So it's the Python. No, for now it's not available. I'm still thinking whether I should make it available or not, or maybe try to expand it a little bit more in the future and trying to make something more like a full-fledged game. Yeah.
How is the enemy AI input? Does it like try to go for specific actions like slow and help and interest with healing, or is it just purely random? Because like
no, it's not exactly purely random. There are some preferences for specific gates at specific phases of the game. At first, for example, the enemy wants maybe more to target its own qubits, then it wants more target the player's qubits and try to other things. But yeah, it can be more sophisticated than it's actually implemented. But then it's already not about technical implementation, it's a problem of game design and game balancing. And maybe I'm a little bit biased myself on that, then it should be like another person who is overthinking the thing. But it's, yes, it's not hard to implement. We can always extract current state vector, seeing the probabilities and try to alter, and enemy would pick some gates that would make the player's life harder. But of course, we also have a goal not to make unbeatable AI. But it's still a game, it should be beatable.
Okay, thanks again. Yeah, floor is yours. Please start.
All right. Hello, everyone. Good morning and good evening, wherever you are. My name is Momin. I'm a student at the IBA. I'm a master's student. And this is the game concept that I've come up with. It's called Quantum Guard. So what the basic concept of this game is that there are qubits in our grid that we have to defend. That's why it's called entangled defense. So there is a prologue to it. There's a protagonist to it, just to make the game interesting for people who aren't very familiar with quantum computing. So there's just a little prologue that comes at the start of the screen where you see that there's an urgency for this kind of thing, where there's a lead scientist on a quantum AI project who has to figure out how to defend her qubits from errors and from solar flares that are coming up. And this is very important for the future of humanity, because this is well into the future, 2051, 2057, 2157, where we have, evolved from our, even compared to that time, this time will probably still be a bit of a primitive time as technology keeps expanding. And again, I'll just touch up a bit on the quantum error types that we have. We have, bit flips, we have phase flips, we have combined errors where the phase can flip itself, or the value of the qubit from 0 to 1 can change on itself. I'm not going to read all of this because, of course, I'm sure lots of people here already know about this. There is, surface code implementation where we're using ancilla bits in the grid to actually detect the errors that are occurring. This is kind of like, how we have a smoke detector in our kitchens or outside our kitchens. If there's a fire in our kitchen, we're not going to go in the kitchen and try to open the door, because then the fire will get out. We have smoke detectors that can alert us on this sort of thing, so that we don't have to, mess everything up. Just like if we actually measure the data qubits themselves, then that means that we're corrupting them, and then there's a whole wave effect, a ripple effect that happens because of it. So the game is simple. We just have a square grid, which I will show you in a bit. We have some bits on the grid, which are basically our vulnerable NPCs that we have to defend. These are our quantum bits that Dr. Ellen Kai has to defend for the future of humanity. We have some tools available at our disposal, which we can use to, you know, measure and detect. And there's some special abilities as well that we'll get onto it as more. As the game starts, you get a well-tailored tutorial which explains the concepts to you as a person who maybe is not into quantum computing or does not have much of an idea on quantum computing. It'll tell you about the special abilities that you have and how they work. Like we have quantum tunneling, we have superposition. These are special abilities that we can use within the game for a limited amount of time, so that we can, kind of figure out how to defend our qubits. And so this is the grid. As you can see, we have stabilizers, we have these errors, these red dots that you can see. These are the enemies, these are the errors. These are our qubits, our stations that we need to defend. And this is their health point. This is their health progress bar that will show you how much of a hit this quantum bit has taken, and how much of the ripple effect has progressed from this particular qubit. We have different levels, of course. We have 5 levels. We can expand it to more, but for the sake of simplicity and because of the limited time, I've tried to keep it as simple. So we have 5 levels. Each level, increases your difficulty, increases the speed of the enemies, and you have lesser number of points available, lesser number of it's kind of like a money system. You have more money, you can buy more things to defend yourself, but as the levels increase, the number of operations that you have available also decreases. This is a sample screenshot. I will show you a live demo in just a bit. Okay, so let me share the other screen. Please hold on. All right, is the screen visible? Okay, let me. All right. So
yes.
Okay. So this is the prologue that we can see in the beginning. We have a log that says, okay, this is the story of it, and this is what's gonna happen. So I'm just going to skip through this. Oh, I'm sorry, I skipped too far ahead, but let me just restart this. Okay. So there's difficulties, there's difficulty levels. If you start as a cadet, you have more resources. The rate of errors is slow. You can only get 2 error types, like the X and the Z type of errors, the phase flip and the bit flips. As you change your difficulties here, then of course you have limited resources, the enemies move faster, and you have more errors to defend. So I will choose engineer or maybe cadet. I'm going to skip the tutorial for now because limited time. So this is our level 1. The quantum memory is under attack. We have to deploy basic error correction protocols to defend ourselves. So, okay, this is a bug that's in the game that was identified later on. But let's see. So you see how there are data qubits uh, in our grid, and we're trying to stabilize and figure out how to do them, and we're measuring them, but at a cost, just like in a real quantum world scenario. We have limited operations available, and I'll show you how these are our special abilities. We have quantum tunneling that has a different cost. We have entanglement cost as well. This is all timed, by the way, so that no one is left doing it indefinitely. Let me show you entanglement boost. The range has doubled. This has a specific range of grids that it can look up. If I do superposition, then you have more stabilizers in 1 or 2 places at the same time, similar to how qubits behave, and so on and so forth. The levels keep increasing and things keep going on, and yeah. So the way to end the game is simply just that you go through all the levels, you figure out how it works, and then eventually you will come at a point where you have a score. There is of course future directions in this, and I would like to present that also. Uh, there's room for adding more topological quantum codes like the toric codes. We can have multiple players, we can have high scores, we can have a 3D visual system. There is a lot to be done in this game because there's a lot to expand, because this is an area of quantum computing that's very interesting, and it's easy to simulate in a game because it's like defending against enemies. So yeah, if there are any questions, or if there is this was just about the game, if there are any questions regarding it, please share, and I would love to answer.
Thank you. We can get one question.
Hello guys, I am Ateeb and I will be presenting my game called D&D Duelist. So D&D Duelist, Dungeons and Dragons Duelist is basically a quantum inspired card game that forces you and your opponent to duel against each other using cards as the main means. Each card embodies some quantum principles which we will eventually see later, heavily inspired by Dungeons and Dragons with touches of sci-fi and some marvelous scientific flair. So the game flow of this in itself is it's a turn-based game. Let me actually show this to you. So this is a turn-based game, and each turn you can play a specific card against your opponent. In order to win the game, you either have to reduce your opponent's health points to 0, or you have to force them to run out of cards first, right? So you always have a limited number of cards available in your deck and in your hands, of course. Now, every card that you see in this game will have at least one of the 4 quantum principles incorporated: superposition, entanglement, tunneling, and phase bias. So if you start with superposition first, while almost every card again has superposition, there are 4 fundamentals we can go through. Collapse barrier, which basically either gives you a shield or takes you have you take 3x more damage. Duelist paradox, deal 6 damage or heal yourself for 3. Magic missile, deal 6 damage yet again, or be dealt 3 damage by self. And then Thanos snap, which is again inspired by Marvel, either reduce the cards in your opponent's deck by half, or have it reduced by half in your deck. And I actually want to show you a quick demo for this. So we will see. So for example, the very first card that's been played is Duelist Paradox. All of the cards will be in a state of superposition and will be measured or will collapse into a specific state once you play them. So the red character on the left plays Duelist Paradox. He got healed for 3 HP, right? The card collapsed into heal. Oh, sorry. Yeah. And then when the white character played it, it collapsed into a damage. The second one was Magic Missile. Again, the red character dealt damage to white, but when the white character played it, he got dealt uh, damage to himself, right? And then we have the third card, which gives you a shield, or you take 3x the damage. And we will see this in action right now. So we have a fallen spell which destroyed the shield, and then we have yet again a fallen spell that made you take 3x the damage. The final spell is Thanos Snap. Dust particles appear and disappear on whoever's side's deck got reduced, right? So in this case, the card backfired on us. When we played it, our deck got reduced by half. In the case of the white character, when he played it, it was in his favor and against us. So this is superposition and how we incorporated it. And of course, when you are playing superposition, right, you might have this thought that, okay, now I maybe want to favor a particular state more. So this is where phase bias comes in. In phase bias, we favor a particular state by rotation, using the rotation gate. So when we play this card, we can choose a specific card and then choose a state which we favor for. So in this case, we said that, okay, we want to damage ourselves. It's not a deterministic, it's still probabilistic, right? So phase bias does this. The next thing that I want to show you is quantum tunneling. So quantum tunneling, as name indicates, is basically when you have a shield on, there you can play the quantum tunneling card to actually bypass that shield. Right? So for example, the red character has a shield on right now. The white character plays the quantum tunneling card. It is active. He attacks the red character right now, and you can see the attack tunnel through. So the shield remains as is. It's not destroyed, but the attack actually managed to seep through the shield. Now, the last thing that I want to demo to you is actually quantum entanglement. So this is more interesting because there are two cards entangled. This one is called elemental affliction. So elemental affliction is in a superposition of four states. When you play it, it will collapse into one of four elemental spells: fire, water, earth, or wind. And then you have also a weather system in game. So you will see rain happening, you will see earthquakes, you will see heat waves, and of course you will see tornadoes. Whenever you play elemental affliction, you will automatically change the weather in game. And we'll see how this happens. So for example, in this case, we just played this card, it collapsed into the earth stack, and you can see the earthquake happening. And you'll see why weather plays a critical role. We did a water elemental attack and it started raining. We did a fireball and it started a heat wave. And then when we did a wind attack, it introduced tornadoes. Now, why is that important? Elemental affliction in itself only does 2 damage per turn for the next 3 turns. However, if your weather matches with the type of elemental attack, so for example, there's a tornado going on and you also do a wind attack, right? So then you triple your damage. So we use entanglement to combine our card with the weather system in game to introduce more combinations that you can do. Sorry, you said something?
All is fine.
Okay. And of course, because entanglement is bidirectional, you can consume your turn to play the weather card, right? Change the weather. It's a high risk, high reward again. And then the next turn, you can play one of the elemental cards, for example, winds, to actually damage your opponent more. Yeah, and this is it. So thank you to Dr. Gibran and Dr. Abuzer. And then these are some of the assets credits we used.
Yeah, great. Thank you.
So, hello everyone. My name is Rabia Khalid, and I have created an educational content on quantum cryptography as my project. So, the reason for choosing this project is because secure communication is the backbone of all our digital world, and quantum technologies are shaping its future. So, while there are many papers and tutorials out there, but my project provides a clear step-by-step explanations with quizzes and live Python notebooks so that the learners can not only read about the ideas, but actually try them out to see how attacks work and test defenses themselves. So the project is structured into 5 chapters. It starts from the very basics all the way to the future of secure communication and where it is used in real world. And each chapter ends with a short quiz to reinforce the learning. I have also included some hands-on Python notebooks with visual simulation inside them for main concepts that are covered in the chapters. So if you run into any tricky terms while reading this whole, there's a glossary at the end to help you out. And you will also find helpful visual diagrams and tables for better engagement and a list of references if you want to dive deeper into it. So next, I will give a brief summary of each chapter that I have discussed overall the project. So the first one is Introduction to Cryptography. So it basically lays the foundation for everything that follows. And the key question here is, what is cryptography? It is simply to keep your communications secure. So let's say there are 2 people, Alice and Bob, and they want to send messages to each other. Cryptography stops an attacker, Eve, from reading or changing their conversation by keeping the messages private and untempered. In the ancient times, people used different schemes like Caesar cipher which shifted each letter by a fixed amount. Though it was clever at that time, but it's very easy to break. And attackers could try all possible shifts and in seconds and read the message. So the weakness led to modern cryptography, which replaces simple shifts with mathematical algorithms. So instead of just guessing shifts, attackers now need to solve the hard math problems like factoring very large numbers or computing discrete logarithms. These were impractical tasks for the classical computers to perform as it takes really long time. And then a new challenge arrived, quantum computers, which can solve these hard math problems much more quickly. So to meet this threat, we are moving towards quantum cryptography, which relies on the laws of quantum physics so that anyone who tries to eavesdrop our quantum signals will change and we can stop those changes. This gives a brand new way to keep our secrets safe. That I have discussed in the second chapter. I have explained how quantum physics secures communication. And by now we know that classical encryption relies on hard math problems, but quantum computers can easily solve those quickly. So quantum cryptography steps in to fill that gap. Now, instead of hiding a message with math, we hide them in the behavior of quantum particles like photons, and we send each key bit as one photon tilted in a specific direction. So, for example, if there's a series of zeros and one, so the up can mean zero and the sideways can mean one. The magic is that anyone who tries to take a peek at our photon, they actually changes it. So if there's an attacker Eve who intercepts the message, the photon, and measures the photon, she disturbs the state of the photon. And later, Bob and Alice can compare a small sample of their results over a normal channel. So if they see there are more errors than expected, they know that someone was spying. Also, this chapter discusses three main protocols, BB84, E91, and B92, and each protocol is paired with a hands-on Python notebook for visual simulations. These are the Google Colab notebooks. You can easily find that out in my repository. And you can play Alice, Bob, and Eve by sending photons, making measurements, and spotting any interference yourself. So this provides an interactive experience to understand how quantum rules protect your key. Now the third chapter explores real-world challenges when you actually build a QKD system. So in theory, quantum key distribution is perfect, but in practice, it can run into real-world challenges. The first challenge is our photon loss. Fibers absorb photons over distance. So in free space, like free space links actually suffer some turbulence. That means many of the particles Alice sends to Bob never actually reach Bob. And even photons that agree can get mangled by noise, such as temperature fluctuations in fiber or background light in free space channels. So these errors look very similar to eavesdropping. So we have to very carefully tell the difference. And in the rest of this chapter, I have explored how to measure and compensate for losses and noise. Now we turn towards post-quantum cryptography. Our current encryption stands on math problems that are hard for today's computers, but quantum computers can solve those problems quickly, putting all our data at risk. So we need a new defense that even quantum machines can't break. Post-quantum cryptography replaces those old math problems with new ones that remain tough for both classical and quantum computers. Now, these schemes can run entirely on an ordinary hardware, your existing laptop or server. So there's no need for any special hardware. I have highlighted four main technologies in this chapter that are lattice-based cryptography, hash-based signatures, code-based cryptography, multivariate schemes. So these all post-quantum algorithms can slot right into your existing security protocols like TLS for websites, VPNs, SSH for remote login. And we can even upgrade our networks today and be ready for the tomorrow's quantum threats. Now, in the last chapter, I have discussed the real-world application of quantum cryptography big banks and financial institutions also use QKD links to keep their money transfer safe. Hospitals use it to protect patient records, and governments set up quantum networks for top secret communications. Beyond Earth, satellites are now in the mix, and a Chinese satellite showed we can send secret keys across more than 1,200 kilometers of space. Now, that's a huge step towards quantum internet, which is a worldwide web of satellites and ground stations sharing unbreakable keys. Here, I've also mentioned how hybrid systems where classical and quantum methods work together. And looking forward, researchers are also exploring quantum secure direct communication, which skips the separate key steps entirely and embeds the secret message directly in your quantum signals. So together, these advances points to a future where our data is locked down by the very law of physics, offering a security that no computer, classical or either quantum can break. So yeah, that is it. Thank you.
Good afternoon, everyone. I am Maz Batla here with my group partner Ali Mohammed. We are excited to present our project Quantum Feature Encoding and Dimensionality Reduction. Okay, so the goal of our project was to explore how quantum techniques can be used to pre-process and reduce the complexity of classical data before applying it in machine learning tasks. Over the course of this project, we developed 4 independent yet connected modules, each structured as a Jupyter notebook, combining theory and hands-on code implementation. Each notebook builds upon the previous one, taking us from fundamental concepts like quantum data encoding all the way to more advanced applications in quantum machine learning pipelines. Okay, so in classical machine learning, feature encoding and dimensionality reduction techniques like principal component analysis or kernel methods are powerful, but they can become resource intensive when dealing with high dimensional or complex data. Quantum methods promise exponential feature space expansions and natural support for entanglement and superposition, properties that classical systems lack. In our project, we incorporated quantum encodings, variational circuits, and quantum neural networks to explore how data can be processed more effectively at a quantum level. This hybrid approach not only enhances representational power but also integrates smoothly with existing classical ML workflows. Okay, so for Notebook 1, it focuses on quantum data encoding, the foundation of our entire pipeline. We explore different ways to represent classical data as quantum states using methods like angle encoding and amplitude encoding. The theory explains how qubits can be rotated to represent data features, and the code section visualizes these transformations using block spares. This module introduces learners to how classical vectors can be transformed into quantum representations, forming the input for quantum algorithms in later stages. Okay, moving on to book 2, we shifted focus to quantum state tomography, which is essentially the process of reconstructing the quantum state of a system from measurement data. We covered the theoretical basis of quantum measurements and their limitations. On the implementation side, we demonstrated how to simulate measurements in different bases and reconstruct the original quantum state using density matrices and visualization tools. This module emphasizes the importance of accurate quantum state interpretation when integrating quantum pre-processing with classical outputs. Over to my partner, Ali.
Okay, so this is Ali Mohammed and I'm going to be continuing from now onwards. So basically in our notebook 3, it introduces quantum principal component analysis, a quantum analog to the classical PCA. We basically explained how quantum PCA can be used to identify the most significant eigenvectors of a quantum density matrix, which effectively reduces the dimensionality of the quantum data while also preserving the key features, which is quite essential. So through simulation in custom datasets, we showed how QPCA can compress quantum state representations and help in denoising and feature selection. This forms a key step in a dimensionality reduction pipeline. Okay, so now moving towards the next notebook. So basically notebook 4, which is a final course-based notebook, which ties everything together into an end-to-end quantum machine learning pipeline. So basically we applied quantum feature maps to construct quantum kernels, use them with classical classifiers like state vector machines and evaluated their performance. We also introduced autoencoders, both variational and hybrid quantum classical for basically dimensionality reduction implementation purposes. Finally, we explored advanced techniques like data re-uploading, variational embedding, and we also explored and implemented quantum transfer learning to show how quantum models can be reused and optimized for new tasks. This notebook is basically where theory meets application in a realistic learning scenario. Now, in conclusion, so basically other than these four notebooks which covers these four main topics, we also had a fifth notebook which basically was a quiz notebook for this module where learners can assess themselves based on their learning of this module. And along with this, each of the four notebooks had code based implementation activities. So after going through the theory and code of each notebook, the learners can test themselves by performing their activities and comparing their solution to the suggested solution so they can evaluate themselves. So basically, in conclusion, our product explored quantum enhanced data pre-processing techniques that can significantly improve the efficiency and performance of downstream ML tasks. We began with encoding methods, ensured interpretability with quantum tomography, reduced complexity using QPCA, and concluded with full machine learning integration. Each module included both theory and working code to solidify conceptual understanding. To reinforce learning, we have, as I said previously as well, we have included practical exercises and a final quiz notebook with MCQs and the answer key. Now, moving towards the future prospects. So basically looking ahead, there are several realistic ways this work can be extended. Firstly, integration with larger real-world data sets could validate the scalability of quantum pipelines. Secondly, incorporating noise-aware training techniques can make our models more robust for near-term quantum hardware. Third, exploring other quantum dimensionality reduction methods like quantum autoencoders with entanglement could enhance compression. And finally, refining hybrid frameworks using tools like Qiskit Runtime or Pennylim could improve execution efficiency and cross-platform integration. So yeah, this is it from our side. Thank you.
Yeah, thank you very much.